My name is Zachary Cutlip, and I'm going to be talking to you today about hacking SOHO routers. And before I actually get into the meat of the presentation, I just want to give a couple of shout-outs. First is my company, Tactical Network Solutions. At TNS, they let me hack on shit. They kind of let me hack on mostly whatever I want, and they also pay me money to do that. I don't think they figured out that I probably would do it for free. So TNS is a pretty sweet gig, and I appreciate everything they've done for me. Also, my friend and colleague, Craig Hefner. When you sit next to Craig every day, it's a little bit like cheating because stuff that should be hard just kind of magically becomes easy whenever Craig is around. So I really appreciate all of Craig's help on this. All right, so what am I going to be talking to you about today? Specifically, I'm going to be going into some novel uses of SQL injection that you may or may not have thought about. I'm also going to be describing the actual mechanics of how buffer overflows work on the MIPS architecture, because there are some differences there between MIPS and some other architectures that you may be familiar with, like x86. I'm also going to be dropping some O-days on Netgear routers because O-days make every talk a lot more fun, so I'm going to give you some O-days. And I'm also going to be sharing some embedded device investigation techniques that have been useful to me, and I think may be useful to you if you're investigating SOHO routers and other types of similar embedded devices. After all that, I'm going to do a live demo for you, assuming that the demo gods are with us and nothing goes wrong. So I know whenever I go to a talk and it doesn't somehow end in a root prompt, it's almost like the talk didn't even happen. So I'm going to do my best to give you a root prompt. If we have time, I'd like to take some questions here in the big conference room after I've done everything. And either way, if we have time or don't, there'll also be questions in the track 4 Q&A room after the presentation. All right. Now, I want to say that I had to be pretty brutal with what I could and couldn't put in the presentation just due to time constraints. So if you find this talk to be interesting, there's a lot of material in the white paper that I think you should have on your conference CD. So if you're interested and you want to know more, please read the white paper. There's a lot of stuff in there that I thought was relevant, but just couldn't make the presentation. So why do we attack SOHO routers to begin with, these little kind of inexpensive consumer-grade devices? Well, a successful compromise of a SOHO router gives the attacker a really privileged vantage point on a user's network. For example, it exposes potentially multiple connected users to further attack, and it also exposes multiple users' internet-bound communications to interception and even possible manipulation. In addition to that, it's certainly not unheard of for people to plug these devices into their work networks for a variety of reasons, some legitimate, some not so legitimate. But at any rate, a successful compromise of a device on a corporate network can kind of serve as a side door into an otherwise well-defended network. The specific device I'm going to be talking to you about today is this Netgear WNDR 3700. And this is actually a really popular device, and if you go on Amazon or Newegg and kind of sort by the number of reviews, this device is easily in the top 5 and maybe even a little bit better than that. It's popular in part due to, besides being a Wi-Fi router, also has some extra features on it, right? So if you plug in a USB drive with music and video files, it'll actually serve up those files over the network. If you have a network-connected television or a PlayStation, it could actually discover that multimedia and play it back for you. It's also a file server, so if you have other computers on your network, it'll serve up those files via Samba. So it's got some interesting features that make it pretty popular. And in fact, here's one particular review on Amazon that kind of suggests that there's actually a lot of fun to be had with this device. So that's pretty promising. Now, besides the 3700, I also downloaded the firmware for the 3800, 4000, and 4400. And I looked at the most recent 2 firmwares for all of these devices. And I did a little bit of disassembly in IDA Pro and just some static analysis. And at least based on my initial analysis, these other devices are also vulnerable to the same exploits that I'm going to show you today. Now, when you get a new toy, kind of one of the first steps you can do to just in your analysis is take it apart, right? And just see what good stuff you find on the inside. And in particular, we find on this device a UART header, which is really awesome because you can connect up a UART to USB adapter and then use a terminal application like Minicom to get yourself a root console on the device. And that's really useful for debugging some more complicated exploits like one of the ones that I'll show you later. In addition to that, we also have a USB port on the back, right? Because it's a network-attached storage server, so you have to be able to plug a USB disk into it. Well, that's useful for us because the application I'm going to be talking about creates its database on the USB drive if there's a drive plugged in. So it makes it easy to get the database off and onto your workstation for analysis. Also, it makes it easy to put a debugger on the USB drive and plug that into the router rather than having to transfer the debugger over the network in some way. So it really simplifies analysis in a couple of ways. Now, one of the first steps for analyzing the software on the device is just go to the manufacturer's website and download the firmware. This is generally available for free. Now, I'm not going to go into the details of unpacking firmware. That's actually covered at length on Craig's blog. So if you want to know more about that, I suggest you check out Craig's blog. He covers all manner of topics related to hacking SOHO routers and other embedded devices. And there's a picture of Craig right there. I think he actually maintains his blog using a soldering iron. I don't know how he does that, but Craig's one crazy dude. So we download the firmware, and one of the first things we can do is extract out the operating system kernel, and we see that we're running Linux. Now, this is really kind of a lucky find because from an analysis perspective, it opens up a wide range of tools and techniques that you can apply to the system rather than having to sort of start from scratch, developing your own techniques for analyzing a proprietary OS like VxWorks or something like that. It's also advantageous because once you compromise the device, now you have a wide range of attack tools that are at your disposal that you can upload to the device, and they work on Linux. So all of the kind of knowledge and experience and tools you have for Linux are easily portable to this device. Once we extract out the SquashFS file system in the firmware, we can actually go through it and see what all applications and programs are on the device. And one in particular stands out. It's this mini DLNA application. Now, why does it end in a .exe extension even though we're on Linux? I don't know, and I don't know if anyone knows. But that doesn't matter because at any rate, we're dealing with this mini DLNA application. So what is DLNA? Well, DLNA stands for Digital Living Network Alliance, and it basically refers to a set of specifications that your gadgets can use to share multimedia files with each other. So if you put some multimedia files on this device and your network-connected television or PlayStation can discover them and play them back. But more importantly, what DLNA represents for us is attack surface, right? Any kind of extra features above and beyond the core routing and Wi-Fi functionality are additional opportunities to find yourself some O-days, maybe write up a paper, and maybe submit that paper to a security conference, right? So it's just additional opportunities to find some vulnerabilities in the device. Now, if we go online and just see what existing information there is about the mini DLNA application, we instantly find that it's actually an open source application hosted on SourceForge. Now, I spend quite a bit of time in IDA Pro in my work, but I have to confess that my reversing skills aren't quite to the point where I don't want to see source code. So this was a really lucky find for me. Now, you can easily get out the version string from the binary in the firmware and see what version you've got of the application, and then just go on SourceForge and check out the right version and just start combing through the source and looking for some low-hanging fruit. This particular application, Mini DLNA, makes extensive use of a SQLite database. So it's worth talking a bit about SQL injection. We normally think of SQL injection as a means of accessing sensitive or valuable data. Maybe you want to exfiltrate some data or tamper with some sensitive data. But what if the data in the database isn't sensitive or valuable in any way? Well, I would submit it's still an opportunity to compromise some developer assumptions. And you know what happens when you assume, right? You end up looking like an ass. So we can just start combing through the source code and looking for some suspect SQL queries. And we find a number of potential opportunities for SQL injection here. And one in particular stood out, and let's take a closer look at this. Now, what this function does is when your DLNA client wants to browse album art, it sends an HTTP GET to the server. And then the server pulls out the numeric album art ID from the URL and then performs a SQL query on it to find the location of that album art on disk. When I was originally analyzing this application, I actually hadn't considered the SQL injection angle. And I was looking for buffer overflows. And as you see here, we have an unbounded sprintf. Unfortunately, this isn't an opportunity to get execution on the system. The most you can do here is crash it, but it is an opportunity for a SQL injection. And just here's a closer look at the sprintf that's happening in the subsequent SQL query. We can simulate what the client does by putting the album art URL into a web browser just with our numeric album art ID. And what happens is the function actually tokenizes on that little dash there in the URL, and then everything after the dash is ignored. And then sure enough, it serves up an album art JPEG to our web browser. So to test this vulnerability to see if we have a working SQL injection, it's just a matter of using wget and giving that same URL to the wget command. And after the album art ID, we just put in our injected SQL query. And here we're going to attempt to create a record in the database that has just a bogus value. And then get the database off the device from the USB disk and then see if your record got in there. And sure enough, there's our record with ID of 31337, made it into the database. So we have a working SQL injection. Now, there's good news and bad news with this injection, with this vulnerability. It's trivial to exploit. We can execute virtually any query we want on the database, so we have full control over the database. But there's not really any valuable or sensitive information in the database. And in fact, even if you blow away the database, it would just be created or recreated by the application. And it only really contains metadata about the music and video files and whatnot. However, if we were to go back and look at that function again, like I said, what's happening is it queries the database and gets a path to the album art on disk. And it serves up whatever that path points to, and it doesn't sanitize the results from the database at all. If we look at the contents of the database at a legitimate record, we see it as literally an absolute path to a JPEG on the file system. So maybe we could create a record in the database that points to something else instead of a JPEG. So we can test this again by going back to wget, and this time we'll create a record that points to, say, something like Etsy password and see what we get. And then a subsequent wget to pull back this fake album art file that we've created a record for. And when you do that, sure enough, you've got the contents of Etsy password, including your admin password. And you might even say that we have a bonus vulnerability here because they're storing passwords in plain text on disk. So that's kind of awesome, right? So in 2 wget commands, I've been able to get your admin password. And at this point, I could easily log onto the admin interface and change around DNS settings or routing tables or even upload a Trojan firmware to your device and take full control of it that way. But I don't yet have remote code execution. And at the beginning of the talk, I promised you a root shell. So I'm not going to stop until I've given you a root shell. So let's keep on going. Now, if, like me, you read Aleph 1's seminal paper on stack smashing and then were disappointed to find that it doesn't really work that way in the real world for a variety of reasons, chiefly among them it isn't 1996 anymore, I can reassure you that you need to look no farther than SOHO routers to find some easy-to-exploit buffer overflows. Okay? And if we just grep through the source code for this one application, we find a ton of potential buffer overflows. Now, if you missed that, let me give you a closer look. That's 265 potential opportunities to get execution in this application. One in particular stands out, and we have this really gnarly function called callback, and I had to trim it way down just to fit it on the screen. But we have an unbounded sprintf here, and this callback function is processing the results of SQL queries. Let's take a closer look at the sprintf. It's generating a URL string from several fields from the result of the SQL query, and one in particular I'm interested in is this album art field. Let's have a look at the actual query whose results we're processing. It's a left join, and looking even closer, we see that album art is a field on the details table, and the query is a join on the details and objects table, and that's just going to be kind of important to remember in a bit when we start developing the exploit. When we look at the schema for the details table, we see that album art is an integer in that table. And there are a couple of things to note about the fact that album art is an integer. First, due to a feature called type affinity, if SQLite can store the value in that field as an integer, it will. If it can't represent it as an integer, it'll just store the raw bytes, which is awesome because that lets us potentially store a long string in that field. Also, the function we're looking at attempts to validate the result from the SQL query using the A2I function. Now, if you know how A2I works, you know that all you need to do is pass it a string that starts with a number, and everything after the number is ignored. So this is, in fact, no verification at all and is easy to bypass, so no problem there. Do we have an exploitable buffer overflow? Well, we have full control over the database from vulnerability number 1. If we're going to exploit this buffer overflow, we need to somehow stage our shellcode in the database, and then subsequently trigger a query on the database to pull out the shellcode and cause it to be executed. We have a limitation with our SQL injection, though. Remember I said that it's easy to crash the application with it, so we need to limit it to about 128 bytes per injection by the time you're taking into account overhead from SQL syntax and HTTP syntax and stuff like that. So we're trying to overflow a buffer that is 512 bytes big. So how do you overflow a 512 byte buffer with 128 bytes? Well, fortunately, SQLite gives us the concatenation operator, so it's just a matter of making multiple passes and building up that string as long as you need. In order to trigger the query of this exploit, initially I was modeling a DLNA client in Python using the coherence library. And that was a little bit flaky because the way UPnP and SSDP works, it would take a while to trigger the exploit. Sometimes it would happen immediately, sometimes it would take a little while, and it was kind of unpredictable. What I ended up doing is just capturing the conversation in Wireshark and popping out the necessary SOAP request that actually triggers the application, and then play that SOAP request back using wget and just ditching the DLNA library. So in order to develop this exploit, you're going to need a few things. One is console access to the device via the UART header that I showed you earlier. Also, you're going to need GDB server cross-compiled for MIPS, and you're going to need GDB on your workstation compiled for a MIPS target architecture. In order to test a vulnerability, just attach GDB server to the target process and connect your local GDB over the network to GDB server. Then use wget to stage a couple of records that will satisfy the left join, and then start building up your overflow data in the database. Then use wget to post a SOAP request. So how much overflow data do you need in the database? Well, it's just a matter of repeating this process until you get a crash in GDB. And then to trigger the exploit using wget, you just use this incantation, and that will actually post your SOAP request. When you do that, if you get a crash in GDB, you should see something like this. And what we see here highlighted in yellow is the MIPS program counter containing our data. We also see all of these S registers, which are general purpose registers, also containing our data. All right. So we control the program counter, which means that we control execution of the application. We also control the S registers, which are very useful in a bit when we start developing the ROP exploit. But controlling the program counter isn't the same as actually having a shell on the system. And I have to say, I was probably at this point in like, I'd say a week and a half into my initial research, and I spent the rest of the time, several weeks, actually getting reliable execution to work on the system, because we have some challenges that we need to overcome. So first of all, the stack is randomized. So we're going to have to somehow defeat ASLR if we want to execute stuff off the stack. Also, because we're dealing with MIPS, we have some architecture-related idiosyncrasies that you may not be familiar with, even if you're familiar with other architectures. You may be disappointed to find out that ROP, although it works on MIPS, is somewhat limited, and I'll get into those details in a second. And we also have to deal with some bad characters, not just related to HTTP, but also due to the fact that we're dealing with a SQL injection. We do have some things working to our advantage, though. So even though the stack is randomized, the heap and libraries aren't, and we'll be able to make extensive use of those libraries to find some useful ROP gadgets. Also, assuming we can locate the stack is executable, so we should be able to execute our shellcode off the stack. So how does ROP work on MIPS? Well, the biggest challenge is the fact that all MIPS instructions are 4 bytes long, and all MIPS memory accesses are 4 byte aligned. So what this means for you is that there's no opportunity to return into the middle of an instruction and have that instruction be decoded as some other instruction. And this drastically reduces the number of ROP gadgets that you can potentially take advantage of. However, you can still find some useful ROP gadgets that do things like manipulate registers, load data that you control into the program counter, and even help you locate the stack and defeat ASLR. So how do you locate the stack using ROP on MIPS? Well, here's a sequence of instructions that load several offsets from the stack pointer into registers S3, 4, and 6, and then subsequently jumps to whatever is in register S0. Now, remember that we control all of the S registers, so it's just a matter of making sure that S0 contains the address of yet another ROP gadget that jumps to whatever is in S3, 4, or 6. And then that gets you back into the stack where you can start executing shellcode. We also have to deal with this issue on MIPS of cache coherency. Now, MIPS has 2 parallel caches, one for instructions and one for data. And your payload was written to the stack as data, which means that it's sitting there in the data cache until that cache is flushed. So you can't actually execute it yet until you flush the cache back into main memory. So how do you do that? There are a couple of ways. One is you could write a massive amount of data to the stack and fill up the cache and force it to be flushed. But you might not be able to overflow a buffer with that much data. Fortunately, Linux provides a cache flush system call. And I believe if you check the man page for cache flush, I think it tells you that it's only implemented on MIPS. So this is actually going to be pretty useful for us. And then assuming you can set up the parameters to cache flush properly, then it's just a matter of wrapping into it and forcing the cache to be flushed. We have to deal with bad characters, which is not an original problem, right? So spaces break HTTP, null bytes break strcpy and other string handling functions, but we're also dealing with a SQL injection, and SQLite has its own bad characters that it'll interpret unless you escape them. Fortunately, SQLite provides an escape sequence that you can use, so anytime you have one of those bad characters in your shellcode, you just escape it with SQLite's escape sequence. Another problem is MIPS's NOP instruction is all null bytes, which sucks because, of course, null bytes break string handling functions. But that's actually pretty easy to deal with. Just use some other instruction that doesn't have null bytes in it, that either is inert or doesn't have any effects that you care about. And so whenever you need a NOP, you can do something like that. The majority of the time I spent developing this exploit, sadly, was getting the payload and encoder to work. Metasploit provides you with one payload and one encoder for the MIPS architecture, and I was never able to get it to work. If I would attach to the process with the debugger and then single step through the decoding and execution of the payload, it would work perfectly every time. But if I wasn't attached with the debugger, it would crash the application every time. And I never did figure out what the problem was. What I ultimately did was just develop my own null-free payload that doesn't need an encoder and just ditching the payload that was in Metasploit. Now, if Indianness messes around with your head the way it does me, and we're dealing with a little Indian architecture which makes it even worse, one thing you can kind of do is things like make your callback IP address all 10s so that byte order doesn't matter, and at least do that until you get issues sorted out with your shellcode and then figure out the Indianness later. In a bit, when I show you the exploit, you'll actually see the script staging the overflow in 3 separate pieces. So the first piece is just a giant buffer that contains random data. The second piece is our ROP chain, which is going to overwrite the return address and also stage the address of several ROP gadgets into the S registers. And then the third piece is our connect back payload, which will actually give us the remote shell. Okay. So that said, it's time for a little live demo, assuming that everything goes well. Great. If you'll bear with me for just a second while I change screen modes. There we go. Okay. Okay, so the router's up. All right. So So I'm going to show you a couple of things, actually 3 things. I'm going to show you the exploit where we can extract some sensitive files from the system, and then I'm going to show you the buffer overflow where we get a remote shell. Once we have a remote shell, I want to show you how we can start uploading some attack tools and actually transform this device into an attack platform. So I've rolled up the the exploits into some Python scripts to make them a little bit easier to use, and also to give us a little bit better output. Now, in the slides, I showed you that we could extract Etsy password. Now, that password file only gets created when you plug in a USB disk, because Samba creates it for some reason. So instead of messing with Etsy password, why don't we try actually getting out the entire system configuration? And the system configuration is in VRAM, and it's accessible via /dev/mtd block 14. So let's see if we can request that block device instead. So assuming I'm spelling this right. Okay, dev mtd block 14. So we do that, and what we actually saw here was the script, it deleted the record from the database to make sure it wasn't already in there, and then created our new record pointing to dev mtd block 14, and then gives us a URL that we can use to bring that file back. Okay, so let's see, if we run strings across that, we should have the entire NVRAM from the system, and if we grep for something like password, we start to see things like, WPA passphrase, admin passphrase. So we have the whole system configuration here. Just tons of stuff there, all right? So there you go. So we've got the admin password with a pretty easy to exploit vulnerability. Now the next exploit I'm going to show you will actually give us the root prompt, and I just wrote myself a little callback server that basically is like netcat, but I wrote it in Python and it gives me a little bit nicer output than just netcat. So I'm going to start that up at the bottom window, and then in the top window I'm going to actually run the exploit, which again I've wrapped up in Python to give us a little bit better output than we get with wget. So we'll just run that, and it clears out the database, and then as it's staging each piece of the exploit, it will actually give us a running count of the number of SQL injections we've done. And then when it triggers the exploit, we should see the root prompt come in the bottom window. So staging the payload now. I think we get up to 46 total SQL injections by the end. Yeah, there we go. And there we go. So all right. Yep. There we go. We can actually look at the kernel version on there. But let's actually turn this into a more useful platform. So for one thing, this is a really crappy terminal session that we're in. So let's actually start up a telnet server on here, and then exit out of there, and then telnet back in, and that'll give us a little bit nicer environment. Oh wait, try it again. And that'll give us a little nicer environment with command history. Okay, so I wrote a little program called telnet FTP. On some devices, you'll find that the only service that you have to take advantage of is telnet, but you still want to transfer files to the device. So I wrote this little Python program that will actually transfer files over telnet, and so I'll run that now, and I'm going to use it to bootstrap a TFTP client on there. Now telnet FTP is a little bit slow because it's just echoing the hexescaped bytes of your file over telnet, and so it takes a little while, and I think that the file we're transferring now is about 22K, and it takes about a minute. So you wouldn't want to transfer very large files, but bootstrapping something like TFTP then gives you the opportunity to use TFTP to transfer some larger files. Once we get this file transferred, I'll show you how we can then use TFTP to then pull down a copy of TCP dump and start sniffing network traffic. It should only take maybe 20 or so more seconds. Then once this finishes, it'll actually start up I've actually pasted in a second command that'll start up a TFTP server running on my workstation. Okay. go ahead and copy the next command and get that ready to go. Okay. So it's done transferring. We're now running into TFTP server, paste in the next commands, and we've now downloaded a TCP dump and start up TCP dump. So there you go. So we're now sniffing traffic that's coming across the router. Okay, so go gadget remote. All right, what could have been done in the development of this system to make it a little bit less insecure? Well, I would submit that, like it or not, this device actually plays an important security role on your network. It isn't just a toy, and it isn't just a device whose job it is to serve up multimedia. It's also your firewall. And I think it's important to actually establish some security requirements at the very beginning, and then make sure those requirements are being designed for, and developed for, and tested all along the way. So, for example, this should be capable of self-protection, which clearly it has completely failed at. It also should be capable of providing you some level of network protection, which again, it's completely failed at because I've compromised it and actually turned it against you and turned it into an attack platform. Also, I would just submit better coding practices would go a long way on this device. I gotta say, it's 2012, and I'm a little annoyed for a couple of reasons. One, I don't yet have a flying car. And two, for some reason, we're still using unbounded string handling functions. I mean, can someone explain to me why we're still using stir copies and sprintfs? Have you heard the good news? There are functions that help you do bounds checking, such as this one right here. Not only does it help you do bounds checking, but if you use it right, it helps protect you against SQL injections. And none of these functions are being used in this application. It's just ridiculous. Also, you've got the benefit on this device that it's running Linux, which is capable of privilege separation, and it has a concept of multiple users. Some proprietary OSs don't, but that capability isn't being taken advantage of. There's no reason for this application to be running as root. It doesn't do anything privileged. It doesn't bind to privileged ports. It doesn't need root privilege, so there's no reason for it to be running as root. Now, a lot of people's experience with SE Linux might be it's the thing that you turn off as soon as you install Fedora on your laptop because you don't want it to break your shit. But I used to work for a company called Traces, and at Traces we developed a lot of hardened appliances using SE Linux. And I can tell you, appliance-type devices is an area where SE Linux really shines. You've got very few applications on the device that you need to confine. You have very little direct user interaction, and users aren't adding and removing applications. And if this device were confined with SE Linux, none of the other stuff would even matter. Privilege separation wouldn't matter. It doesn't matter really even how crappy the programming is, because the application wouldn't be allowed to access sensitive files. It would only be allowed to access certain files that are known ahead of time. Also, it wouldn't be allowed to execute programs. So even if I successfully overflowed a buffer, it wouldn't be allowed to execute binsh or establish outbound network connections. So it should be at least theoretically possible to develop a single SE Linux policy and apply it to all the devices in the product line and add and remove SE Linux policy modules as necessary to confine different features. Now, what's the upshot? The developer in this case has assumed that everything coming from the database is well-formed because only his application ever puts data in the database. So how could there be any data there that's bad? Well, we're able to successfully compromise the database and violate those assumptions, and we're able to do that even though the database itself is of low value. So there you go. All right. Now, here's my contact information. So if after Black Hat you have, or I'm sorry, DEFCON, you have any questions, feel free to get in contact with me in one of those ways. And for now, I think we're running early. So if you have any questions now, I'm happy to take some questions. Yeah, yes. Yes. Yeah, that's right. So the question was, the attacks that I'm running, do they only work on the LAN side? Yes, so currently they do. They only work on the LAN side. This process is only listening on the LAN side. However, Craig actually presented a tool a couple of years ago at DEFCON called Rebind that Rebind proxies HTTP requests through a victim's web browser over the internet to the LAN side of the device. All of these exploits are HTTP based. So in theory, this exploit should work with Craig's Rebind tool. In practice, I haven't gotten it to work yet because the JavaScript in the web browser mingles the SQL injection, but in theory, there should be a way to make it work and turn it actually into an internet-based attack. Yes?
Are there any SOHO routers
Yeah, so this is a question that I get a lot. So at TNS, we work with a lot of SOHO routers. Oh, I'm sorry. So the question is, are there any SOHO routers that we can recommend? Well, at TNS, we work with a lot of SOHO routers and find vulnerabilities in them. Unfortunately, one of the problems when you do that is you start to get a little jaded, and basically every router that you see is an opportunity to exploit. I really don't have a recommendation. I know at home, I actually run a custom Linux distro on a small PC, so yes.
So the initial launch has to go through the serial port, right? So you have to have hardware access to the device?
No, you only need hardware access to the device when you're developing your exploit. So you order one of these from Amazon, take it apart, connect up to it, develop your exploit, but the actual exploits just need network access.
Internal LAN access?
Yes, yes, internal LAN access. I would also point out that this device is vulnerable to Reaver, if you're familiar with Reaver. So all you need to do is be on the premises to attach to the LAN and exploit it.
Thank you.
Yes. You bet. Let's see. Yes. So we haven't looked at BusyBox, and BusyBox is really just a small piece of the OS. If you're not familiar with BusyBox, it's a multi-call binary, which gives you a lot of Unix commands. We haven't spent much time analyzing BusyBox itself. BusyBox is pretty well vetted, though. It's a very widely used open source application. I wouldn't swear that there aren't any vulnerabilities in it, but I wouldn't expect them to be as low-hanging as these were. Yes. No, that's not the case. So the exploit doesn't require the USB drive, and the exploit doesn't. You're talking about when I was developing the exploit, and it would crash. So I was trying to use the payload that's in Metasploit, and I could get Metasploit's payload to work if I single step through it in a debugger. I couldn't get it to work without the debugger, so I ended up developing my own exploit that works fine. Oh, interesting. Okay, so the observation is that the debugger itself may alter the memory layout. And okay, thanks. Are there any hands that I'm missing? Okay, there's a hand in the back. We haven't formally made the source available, but I know that a while back I tweeted a link to Pastebin where I actually put an initial version of the program just for shits and grins. So I think if you Google my name or Google my Twitter handle, that Pastebin link should come up. Okay, got a question over here. Sure, no, that's a fine. So the question is, did I look for other vulnerabilities? And I can tell you, yes, we do actually have a bag full of tricks on this device, besides the one that I've shown you today. And I'm not prepared to share those with you. Those are secret sauce. Yeah. All right. Oh, okay, I don't see any more hands. So, what's that? Okay, Q&A 4 is where we're going to be doing some more questions if anyone wants that. All right, thanks a lot for coming.